All right, here's a little bit more bonus material from section 3.1 from OpenStax PreCalculus. In this section, you learned about complex numbers. And really, there's some things related to complex numbers that I just think are super interesting that maybe shouldn't be in the scope of a pre-calculus class, but I feel like I was kind of cheating you if I left these out altogether. So I want to make a little bonus material. And so what I'm going to talk about in this video are what are called quaternions, which is already kind of impressive. Just the name is a little bit crazy, but it gets crazier. So quaternions. Okay, to explain what a quaternion is, I want to start by talking about real numbers. And you're like, yeah, I got that. Real numbers. I'm familiar with what a real number is. Okay, but you can think about a real number as a one-dimensional number. And you're like, wait, well, one-dimensional? What the hell would a number be if it were not one-dimensional? Well, you're probably most familiar with real numbers, so all numbers you think of are one-dimensional. By one-dimensional, I mean you can put them on a number line. Right, there's my one dimension. Here's 0. Here's 1. Here's 2. Here's, I don't know, 0.4. Here is pi. Right, I can put whatever number I want somewhere on this number line in one dimensional. I can order them all. But that doesn't work when you move up to complex numbers. When we're talking about complex numbers, which maybe now you have a decent grasp of, they are not one-dimensional numbers. They're really two-dimensional numbers. In that if you want to plot them all, you wouldn't need a number line. You'd need a pair of number lines. You'd need coordinates. So I could do something like, here is my real axis, and here is my imaginary axis. So I don't know, something like 3 plus 2i has a real part of 3, an imaginary part of 2, so maybe I'd put 3 plus 2i right here. Whereas, I don't know, negative 2 minus I would have a real part of negative 2 and an imaginary part of negative 1. So this would be negative 2 minus I. At any rate, complex numbers are two-dimensional numbers. And even in this section, you learned about complex numbers, and you even plotted a few of them, so you really thought of them as two-dimensional numbers. You might wonder if that's where the story ends. Right, what about three-dimensional numbers, for example? Could I define it? I mean, I'd need another letter, and I'd need fancy names. Like I already used real and imaginary, so like, I don't know what I'd call them. But maybe like 3 plus 2i plus 4j. Could that be a three-dimensional number? Well, if it's a three-dimensional number, I'd have to be able to add 2 of them up. But that wouldn't be too hard. If I had 2 of them, I could add the numbers together. I could add the coefficients on the i's together, the coefficients on the j together. But I'd have to get clever in figuring out how to multiply them, because I'd have to multiply them so that the product of any 2 of these hypothetical numbers would be one of those three-dimensional numbers. Turns out it's not possible. So then what the hell are you talking about? Why are you wasting my time on this video? If we can't get past two-dimensional numbers, then why are you talking? Okay, we can't come up with three-dimensional numbers. However, it turns out that you can come up with a four-dimensional number set, which is pretty wild. A four-dimensional number set. Those four-dimensional numbers are referred to as quaternions. And I'm just going to give you a brief introduction to how they work and a little bit on their history, because their history is super interesting. I won't bother trying to draw a picture because I can't draw 4 dimensions because I'm restrained by this three-dimensional world that I live in. That makes it really hard for me to picture anything four-dimensional. But the nice power of math is I'm not limited to just the dimensions that I live in. I can do more powerful stuff. FYI, the story doesn't end here. Turns out there's these things called octonions. And go ahead, take a guess. I mean, they got to be more than 4, right? How many dimensions are there? Well, oct, maybe you'd think 8, and you'd be right. They're 8-dimensional numbers. Well, you skip straight from 4 to 8. What about 5-dimensional numbers, or 6 or 7? It can be proven that no such number system can exist. Similar to 3-dimensional number system. It's not possible to come up with a number system and have things work out, meaning multiply, divide, add, subtract. And when you put 2 of these things, there's no rules that'll make those work, and it can be proven. Furthermore, there's no rules for any dimensions above 8. So we can work in 1, 2, 4, and 8. You're like, 1, 2, 4, 8. I bet 16 works. Nope. Just 1, 2, 4, and 8. Those are the only possibilities. I'm not going to worry about octonions because they're pretty weird. All sorts of stuff breaks down when you get to them, and they're too complicated to talk about. They don't have a cool history as far as I'm concerned, but quaternions do. So I'm going to focus on these guys right here, 4-dimensional numbers. First, I'm going to tell you their story. And this story is fairly true. What I tell you about quaternions will be exactly true, but the history, again, fairly true. I'm going to try to hit on the key concepts. But everything I actually tell you about the math will be true. I'm a math teacher, not a history teacher. So the story goes like this. In the 1800s, there's this guy, this Irish mathematician. His name was Sir William Hamilton. And he was out walking. So I don't know, maybe this is his house right here. And I don't know why I feel the need to draw a picture, but I've gone this far. This is home. And actually, he was out walking with his wife. And so in my story, they're going out to dinner. And their restaurant looks a lot like their house because that's the only figure I know how to draw. Restaurant. And unfortunately, I don't even know how to spell restaurant, so I'll just write it really messy and maybe you won't notice. Anyways, this dude's out walking with his wife, right? They're trying to get from here to here. And in between, there's this big river. Yeah, okay, there's a river. So what do you do when there's a big river? Well, hopefully there's a bridge. And unfortunately, there was. It's called the Broom Bridge because it's in Ireland. It's spelled all weird. It's like B-R-O-U-G. I don't know. Something weird. But it's pronounced the Broom Bridge. And that's this guy right here. So Hamilton and Mrs. Hamilton are walking out to dinner. Apparently she's pretty tall with a big neck. They're walking out to dinner. They're going from home to the restaurant. And I'm sure she's talking, telling him some story. And him being kind of this aloof mathematician is deep in thought. And what he's thinking about are quaternions. He had been thinking about these, struggling with these for a long time. He thought there could be some four-dimensional number system. And he knew how to add them and subtract them, but he couldn't get them to multiply and things to work out. So she's talking, but he's not even listening, which is kind of unfortunate. So from his perspective, she's not saying anything. She's just talking, and he keeps on walking. And as they're going across the bridge, I guess this is more of a thought here. He has this thought. Hits him like a bolt of lightning. He's really, really excited. Out of nowhere, he solves the mystery of these quaternions. He's like, stop talking, hold up, I just figured it out. She said, well, I was halfway through a story. I don't know that this is really what happened. Again, this is fairly true. He solves quaternions. He figured out the one equation that makes everything work. And he was so excited. He pulled out a knife out of his pocket. I don't know why he had a knife in his pocket to begin with, going out to dinner. But he had a knife in his pocket for some reason. And maybe it wasn't even a knife. Maybe he picked up a stone off the ground. But whatever. The story is fairly true. So in my story, it's a knife. And what he does, he's so excited about this equation that he just came up with that he carved it into the bridge. That he said, this is brilliant. I am going to change history. I just came up with the biggest revelation of this century. I don't know that that's true. I figured out the equation that defines quaternions. And this is what he wrote. He wrote I squared equals, I better make sure I write this right, J squared, which equals K squared, which equals IJK, which equals -1. I'm pretty sure that's what he wrote. He carved that straight into the bridge. And then, he does his mathy thing. He publishes this in journals, and people look into it and figure out that he was right. And it's this huge undertaking, and all sorts of stuff is built off of it. And it's really, really famous. Famous enough that that Ireland, where this all takes place, which is why this is all green, because everything in Ireland is green, was really proud that one of their mathematicians came up with this discovery, I guess. And they put this plaque. If you go there today, it's in Dublin. If you go to Dublin, you go to the Broom Bridge. You shouldn't really do this. If you're in Dublin, you have way better stuff to do. But you can go to this bridge, the Broom Bridge, and what you'll see is there's a plaque, because the original carving is long since gone. It's been a long time. It's weather. It rains a lot out there. It's probably graffiti, etc. But they put a plaque on top of it. In fact, I have the plaque. This is the plaque right here. And it's a little bit hard to read, but I think it says, here, as he walked by on the 16th of October, 1840, maybe, Sir William Rowan Hamilton, which is this guy's name, in a flash of genius, discovered the formula, the defining formula maybe for quaternions. And it was I squared equals J squared equals K squared equals IJK, which equals -1. And it turned out that was the key to multiplying these guys together, this right here. And so when you're dealing with quaternions, you have these four-dimensional numbers. So a typical number in quaternion might be 3 plus 2i minus 2j plus 4k. Fine. This is a quaternion number. And I could add that to another quaternion number, like, I don't know, 1 plus I minus j minus 2k. Fine. These are two numbers, I could add them together. No problem. When you're adding them, just add 3 and 1 is 4, 2i and 1 more I is 3i, -2j, and minus 1 more j gives me negative 3j. 4k minus 2k would be positive 2k. I can add them together. I could even subtract them. Multiplying them will be challenging. If I can figure out multiplication, I can get kind of clever like we did with complex numbers and define division. But multiplication will be challenging. And the reason multiplication will be challenging is because much like I did with complex numbers, I'm going to attempt to kind of foil this thing out. And 3 times 1 is no problem. And 3 times I even, and 3 times j, and 3 times negative 2k, that's no problem. But when you get these cross terms, like 2i times negative j, or 4k times negative j, or even 4k times negative 2k, then what happens? And it turns out that it's all encoded in this little formula right here. That if you have an I times an I, you get a negative 1. If you have a j times a j, you get a negative 1. A k times a k is a negative 1. And I times a j times a k is a negative 1. And the rest of them, which apparently are implied from this, although I like to draw the picture, comes from this. It's supposed to be a circle. If you multiply, now it's hard to see my I times j, you get k. I times j equals k. Because I'm going around the circle. I times j equals k. J times k equals I. And k times I would be equal to j. Because I'm going around the circle. Oh, yeah, k times I equals j, going around the circle. However, what about j times I? And you're like, oh, you already did that. J times I is k. You're assuming that things are commutative. It turns out that when you're dealing with quaternions, we lose commutativity. J times I is not the same as I times j. This number system is not commutative, which is kind of wild. J times I is actually negative k, and it has to be in order for this thing to work out. You can get that from the picture, because j times I, now I'm going against the circle. And when I go against the circle, j times I do get k, except it's negative because I'm going in the wrong direction. Similarly, I times k would be negative j. And which one did I miss here? I did I times k is j, j times I, so I guess k times j is the one I haven't done. K times j will be equal to negative I. And with these facts, which somehow are a consequence of this thing here, I don't know how you could prove that somehow. Probably using this, you could figure out one of these. At any rate, you can prove all these facts from them. That completely defines these four-dimensional numbers called the quaternions. And with quaternions, you can do crazy, and everything works out, like everything that should work out. When you're multiplying these two numbers, and that equals something else, I should be able to divide this one by that one and get this one back. Like I should be able to do all these things. It all works out. And it all comes back to this formula, discovered by this guy as they did this walk right here. That's the history of quaternions. Before I quit this, I'll note that there are octonions. Although now instead of four-dimensional, they're eight-dimensional. So not just i's, j's, and k's. I got 7 more. I get 7 total letters that I need to define these things. And they get even worse. Not only are they not commutative, meaning ij is not the same as ji, they're not even associative. So if you think about what it means to be associative property tells me that 2 times 3 times 4. The commutative property would tell me this is 2 times 4 times 3 if I wanted to mess with this order right here. That's the commutative property. The associative property, you don't even mess up the order. The 2 still comes first, the 3 comes second, and the 4 comes third. And I'm still multiplying them all together, but now I'm going to do the 2 times the 3 and then times the 4. All I do is group them differently. The order's the same. This is the associative property. This doesn't even hold with octonions. Octonions are a mess. Quaternions, somewhat useful. Octonions, really just useful from a theoretical point of view. Wait, how would quaternions even be useful? Well, it turns out that having four-dimensional numbers is really useful. I'm no physicist, so I can't really tell you why, but I think it's got something to do with the fact that we live in this three-dimensional world, so you can kind of use up 3 of them to take the place of the 3 dimensions we live in, and you still have 1 left over. So that extra dimension of your number can represent something like time or like magnitude or something else. You can use that extra dimension however you want. So the way this was taught to me is if you're trying to sink a submarine, if you're a submarine and you're some warmonger, I don't know, or maybe the other submarine's out to get you and you need to shoot them down. You need to know a lot of things. You need to know what direction to shoot. And by direction, you kind of have 3 dimensions to deal with. Is it like up? Is it east, north, to the left? Which direction are we talking about? Well, with 3 dimensions, I can figure out which direction to shoot. You also got to know when to shoot. And I can use my 4th dimension in these quaternions to figure out when to shoot. I can reserve the k dimension to have something to do with time. And somehow that will make quaternions help me destroy submarines. So I don't know how true that really is. But everything I told you about quaternions and complex numbers and real numbers and these formulas are true. So at least this is fairly true.